Carnegie Mellon University's Maysam Chamanzar and his team have invented an optical platform that will likely become the new standard in optical biointerfaces. H has labeled this new field of optical technology, Parylene photonics, demonstrated in a recent paper in Nature Microsystems and Nanoengineering. There is a growing and unfulfilled demand for optical systems for biomedical applications. Miniaturized and flexible optical tools are needed to enable reliable ambulatory and on-demand imaging and manipulation of biological events in the body. Integrated photonic technology has mainly evolved around developing devices for optical communications. The advent of silicon photonics was a turning point in bringing optical functionalities to the small form factor of a chip. Research in this field boomed in the past couple of decades. However, silicon is a dangerously rigid material for interacting with soft tissue in biomedical applications. This increases the risk for patients to undergo tissue damage and scarring, especially due to the undulation of soft tissue against the inflexible device caused by respiration and other processes. His solution, Parylene photonics, is the first biocompatible and fully flexible integrated photonic platform ever made. To create this new photonic material class, Chamanzar's lab designed ultracompact optical waveguides by fabricating silicone (PDMS), an organic polymer with a low refractive index, around a core of Parylene C, a polymer with a much higher refractive index. The contrast in refractive index allows the waveguide to pipe light effectively, while the materials themselves remain extremely pliant. The result is a platform that is flexible, can operate over a broad spectrum of light, and is just 10 microns thick, about 1/10 the thickness of a human hair. We were using Parylene C as a biocompatible insulation coating for electrical implantable devices, when I noticed that this polymer is optically transparent. I became curious about its optical properties and did some basic measurements, said Chamanzar. I found that Parylene C has exceptional optical properties. This was the onset of thinking about Parylene photonics as a new research direction. Chamanzar's design was created with neural stimulation in mind, allowing for targeted stimulation and monitoring of specific neurons within the brain. Crucial to this is the creation of 45-degree embedded micromirrors. We were able to package our Parylene photonic waveguides with discrete light sources using accessible packaging methods, to realize a compact device. The applications for Parylene photonics range far beyond optical neural stimulation, and could one day replace current technologies in virtually E. These tiny flexible optical devices can be inserted into the tissue for short-term imaging or manipulation. They can also be used as permanent implantable devices for long-term monitoring and therapeutic interventions. Additionally, Chamanzar and his team are considering possible uses in wearables. As further options for optical therapeutics are explored, such as laser treatment for cancer cells, the applications for a more versatile optical biointerface will only continue to grow. Current chip-to-chip interconnects usually use rather inflexible optical fibers, and any area in which flexibility is needed requires transferring the signals to the electrical domain, which significantly limits bandwidth. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.